Last 10 minutes, I would like to introduce you to Fourier polynomials and Fourier series. Let's introduce it by first talking about waves and sound. What do I have here? Play sine 2 pi times 400x. X goes from 0 to 5. What in the world? Let's enter it. Make sure we're loud enough. Oh, isn't that pretty? A pure tone, supposedly at 440 hertz cycles per second. It is showing the graph of it. I can also use an ordinary plot to try to graph it. It oscillates very rapidly. If I want to see the oscillations more clearly, I could make the interval smaller like that. That's over 0.1 seconds. So that's a pure harmonic, I guess you could call it. What happens if I add two pure harmonics with different frequencies? 440 hertz, which I think that's middle C, 440 hertz. 880 hertz, that's one octave above, I think, right? Does that sound right? You're playing two Cs of different frequencies, I think, if my music is right. What happens if you graph that over that interval? Again, it looks just like a bunch of oscillations. Over a smaller interval, it gets a little bit more interesting. It's not a pure sine wave anymore. We're adding sines of different frequencies. We get kind of weird oscillations. Let's add in a third tone, 1760, yet another octave higher. I keep doubling the frequency. Three of them. These are all supposedly Cs, which I wasn't really thinking about in the first class. If you wanted to like get a chord in there, you'd have to do other kinds of frequencies. What's the graph this one look like when it's close in? It's a little bit more wild. Things can get really interesting. Well, I guess this is more of a harmony here. Yeah, you can see that. This can get even more wild. Okay. Maybe a bit tough to tell what's going on there exactly. Seeing a little bit of like an overall oscillation in addition to the rapid oscillations. That gets more extreme if you're really close in frequency, 440 and 441. It's a louder, softer, louder, softer. It's called a beating phenomenon. And over, you see the oscillations like that, indicating the beating. We can also have dissonance. 440 hertz and 473 is kind of dissonant. And I mean, it's still showing somewhat of the beating oscillations. Anyway, so you know, or you should know from physics, that sound is made by sound waves, which are vibrations effectively in the density of the air molecules. And your ear picks those up and your brain interprets them, like me talking, as information, as sound that you can maybe even understand. With Fourier polynomials and Fourier series, you're trying to effectively analyze such signals, you could call them in general. And the signals can be strange, even like a triangle wave whose graph looks like that. What does that sound like if we played at a faster frequency, at least? A little sharper. That's a C tone, but it's kind of a sharp timbre, I guess, because these corners are sharp. I don't know if that's the reason or not. Essentially, Fourier polynomials try to take linear combinations of cosines and sines of different frequencies to approximate the curve. The coefficients, effectively the amplitudes of those things, are found by doing integrals of all things. Calculus 2. integrals of functions times cosines and sines at different frequencies. They're typically called A and B. These B's are coefficients of ultimately some sine functions. You do see they have interesting patterns here with this triangular wave examples. They're all multiples of a fraction over pi squared, amazingly. I am adding those things, putting those coefficients in front of different sines at different frequencies, K changes here, and adding the results to get what's called a Fourier polynomial. Here is what fx20 looks like. It's going to do the calculation. There it is. That's called a Fourier polynomial, even though it's not a polynomial. And then I can effectively graph such things. The triangle wave you see is in red. The blue graph is a pure sine wave, just one term in the sum. But if I keep increasing n here, I'll get more and more terms in the sum, and it approximates the triangular wave better and better. You can also compute something called the energy of the function, which is related to the energy of the sound wave, for example, and find out what's called an energy spectrum, which is essentially discrete information about the signal. Most of the energy is in what's called the 0th harmonic here, I believe, or it's the first harmonic. Okay, what this is all working toward is actually taking discrete information for sounds and converting it to analog information back and forth. It involves something called the fast Fourier transform, which is one of the most famous algorithms out there. Very, very useful. Whoever created the fast Fourier transform probably became a millionaire. He probably patented it. I'm not sure about that, but I'm guessing about that. It's used everywhere in electronics, signal processing. How do you get the speaker to play a sound? You got to use essentially digital information translated into analog information. Fourier series have other applications as well. The thing that comes to my mind is partial differential equations. And in particular, the most famous partial differential equations have names: the wave equation, the heat equation, and Laplace's equation. Wave equation for modeling wave motion, heat equation for modeling heat diffusion, Laplace's equation for lots of other things, including, for example, electrostatic potentials, but other things too. They're the most famous partial differential equations, and you need Fourier series to understand them and solve them. In diffie-q with linear, we do that at the very end of the course. If you want more depth on that, you take something like math methods of physics.